So first I would really like to thank organizers, particularly Paul Nugget, for this invitation. He said this is my first time in Ireland, probably one of the few, maybe the only country of Europe I didn't manage to see yet before. And I'm very thrilled and excited to be here in front of you, especially because you're all teaching physics. I must say just one correction my research background actually is in magnetic resonance imaging, and a lot of time I spent, had the privilege to spend with Sir Peter Mansfield, late first Sir Peter Mansfield, inventor of magnetic resonance imaging. And later I switched to physics education research. But now I'm doing physics education research, and I'm preparing high school physics teachers for Slovenia. And I'm preparing all high school physics teachers for Slovenia. Slovenia has only 2 million population. There's only one place to get this degree. And so you know how it is. If anything goes wrong, at least in Slovenia, they know whom to blame. So, yeah. The title of my talk is Active Learning that Helps Students Think Like Physicists. I will start with something that probably you heard in different contexts. No. Is it working? Yes. To learn anything, people need to be active participants in the learning process, not passive observers. I'm sure you heard this many times. This is actually the essence of active learning idea, interactive engagement of students and so on. And I want to point that this is not just some statement based on gut feeling. Actually, this is a statement based on a lot of research. And this research is around for quite some time. Here are just examples of few most well-known papers that describe results of the comparing traditional teaching to teaching where students are interactively engaged on thousands and thousands of students in different institutions, different countries even. And all these results robustly show that traditional teaching, and by traditional teaching I mean where students are listening, observing demonstration experiments, making notes, and the best lecturers are lecturing, and students only later go to labs and do some experiments to verify the theory that they had heard before, that this kind of teaching only results to, let's say, some very moderate teaching learning gains. While active learning methods, and yes, there are different and you can apply them also in a wrong way, but if applied properly, lead to much better learning gains. So the research in this part shows that active learning is much more efficient. On the other hand, we have a lot of new knowledge in brain studies and in cognitive science recently that shows how we actually learn people. And from this research, we also get some very new information, and I advise all of you to get this little booklet by James Zal, The Art of Changing the Brain, written for teachers. It's an excellent book, changed my life. And here are just 3 very important points from this book. First, learning is physical. This means that when we learn actually physically, our brain is changing. And how do we know? There are several methods like functional MRI or positron emission tomography that shows changes in the brain when we are learning. The pictures look something like this, maybe. So this is first important thing. That is not something untangible. We can see changes. And once we can see changes, we can also then get some objective evidence what means learning. And from this we know that we cannot erase existing neural networks. This is a very important thing. So cognitive conflict actually is not something that works in an essence that many people understand it. Like we will bring child into the cognitive conflict, and then when he will realize that this explanation is better than his own explanation, he will switch. No, it doesn't work. We can only build new neural networks and enhance them and create new paths and strengthen them, but we cannot erase the old ones. And that's also explanation why even experts, when you give them a certain problem, qualitative problem in physics, sometimes will give it a wrong answer because that path is not established yet. So we are only when we are in a situation that is new for us, our brain will go that old way which they used to go. And building new paths and building on the existing paths is something that is productive. And third, active learning is something, active testing of our ideas is essential part of learning. So if active testing is not purposefully included in our teaching, it means that we are not actually controlling one part which is essential. Traditional teaching, where students are listening, making notes, and then comparing this knowledge with their previous knowledge, trying to give meaning to it, misses this part. Active testing is not built in the lesson. Students test their ideas then in their own way. They go and ask the colleague, what did he mean? Did he mean this? And we say, silence, don't talk now. So this is something that if we can purposefully include in our lessons, we will improve learning significantly. My mouth is getting dry. And then, apart from the research, there's also our societies, the expectations of the labor market, of economy and all this that shapes our teaching and our educational systems. I picked this document released last year by Organization for Economic Cooperation and Development. This is a position paper on what knowledge, skills, attitudes and values will today's students need to thrive and shape their world in future. Signed by respectful representatives of many countries, including Ireland and Slovenia. What is written in this paper is this, that in addition to the disciplinary knowledge, this is the content of physics that we are teaching, and the procedural knowledge, which is acquired through practical work, we have to also teach or help students to learn so-called epistemic knowledge. This means how to think like a historian, how to think like biologists, how to think like physicists. And we cannot learn how to think like physicists by reading Einstein, Feynman, Hawking. We have to be put in a situation where we develop this kind of a thinking. So epistemic knowledge is something that is becoming more and more important because it's something that gives you ability to understand how physicists know what they know. And then as a citizen, when they propose me some new ideas for some technology or something, I can at least say, well, they usually look for the evidence. Can you give me the evidence? So once you know how in a certain discipline the knowledge is built, you are much more, let's say, competent in judging if some new ideas are make sense or not. Michael Waldrop goes so far in his paper in Nature that says that at this point it is unethical to teach in other way than active way, so interactively engaging students. Okay, so this I can then summarize in two major challenges. One challenge, how to achieve active engagement of students in all steps of learning, and second, how to help students to develop epistemic knowledge. These were two ideas that I gradually absorbed, and for the last 19 years I'm preparing future physics teachers, and I was slowly trying to incorporate these ideas and build on them in my teaching, preparing future high school physics teachers. My passion were always experiments, and so I also try to develop new experiments, activities based on experiments, test those activities, publish papers about that. But also I went around the world and learned different interactive engagement methods from people that were experts in this field and proved to develop things that are very useful. And I thought that then if I bring home this and use my ideas and present all this to my students, that later when they go to schools, they will be able to use these ideas and maybe build their own approaches or use one of the approaches that I showed them and really do the active engagement of their students. Unfortunately, this didn't happen. I realized when I was observing my students after that they were not able to put these fragments together in some coherent approach, and that they ended up as being pretty much traditional teachers lecturing, as if they never learned these things before. So in a way I realized, and this was like probably 9 years ago, that I was missing some coherent framework for teaching and learning that would help me to prepare future physics teachers to use one coherent approach consistently, which would be aligned with these new trends that I mentioned before, but also with my own experimental ideas of physics, which I, as a teacher, wanted to pass to them. So I wouldn't be telling you about this if I didn't find a framework, but instead of just explaining you the framework, which would be in contradiction with what I'm telling all the time now, that you have to be actively engaged, I will ask you to participate in short activity which will illustrate you what I mean. So now imagine that we started a unit of mechanical waves, and now I want you, my students, to construct the concept of superposition. I don't say anything about superposition. I don't come to the classroom and write superposition on the blackboard, but I start with a motivation. I know that students are using headphones, and today many of these headphones have noise cancelling feature. So we start with the motivation. How do noise cancelling headphones work? I say nothing about this, but I say that by the end of this lesson, or maybe unit, you will be able to understand at least approximately how the noise cancelling headphones work. And then I'm trying to bring back to this idea during the next lectures. And then I start with a simple experiment, which we call observational experiment, put students in groups and ask them to take slinkies and make two equal amplitude pulses on opposite sides of the slinky and observe what they see and describe what they see. And students are doing this. First, they observe this in real time. You all know this experiment, so this is in real time. Sometimes they have their mobile phones. They take high-speed videos of this same phenomenon, observe it also with this. Or you can have this on your own computer or on YouTube, the high-speed parts if you want. And then after that, so this is what they observed. And now I ask them, devise possible explanations for the observed behavior of the two pulses. So I now would like to ask you to talk to your colleagues and come up with what are the possible explanations for this, what we observed. You have 1 minute. How could students, or how would you explain this? What happened?
It looked like they bounced.
They bounced, yes. That's exactly what one of the explanations from students are when you start listening them, and they have in mind some kind of a collision-like process. Yeah. What is the other possible explanation that they might come? They pass through. They pass through one each other. Actually, this is even written in a little paper by Michael Whitman and colleagues in Physics Teacher, a little research on how students respond. So we end up with two different explanations. We call them bounce-off and pass-through explanation. And now think of that goal. We have to teach our students also how to think like physicists. So what physicists do when they have different explanations for the same phenomenon, what they do? They run experiments. They run some very different experiments sometimes to test these ideas. So now this is usually the most creative part for students, as you will experience, propose testing experiments. What kind of experiments we could run to test which of these two explanations is correct? Please talk to your neighbors and come up with ideas. Ready? Yeah, can I have some suggestions?
Different direction, different phase at the start, going up, going down.
Yes, agree. Somebody else have this idea to send two pulses of different sign of amplitudes. Yeah?
Or big one, little one.
Or one big one and one little one of the same sign of amplitudes. Perfect. So we have two excellent testing experiments. And what I would do when I was, let's say, before a traditional teacher, I would say, here, I show you and let's see, and now you see which one is correct. But now I learned, no, I'm not doing this. I'm asking you to predict, before I run the experiments, predict the outcomes of these experiments based on these two explanations that we built before. So if the bounce-off explanation is correct, and I send one large parse from this side and a little parse from this side, what will happen? The large one should go this way, the little one this way. Of course, this is trivial for us, but when students have to do predictions for the outcomes of testing experiments before they see the outcomes, they are connecting their previous knowledge with this new knowledge and making more coherent knowledge altogether. Again, if I have a negative pulse here and positive here, and I send them, the positive should go on this side if the if the go-through explanation is correct, or positive should go back if the bounce-off is correct. So all this is something, the predictions come before the outcomes, and students are encouraged to use all kind of representations to make sure that they clearly predict and discuss and share their ideas. So this is something what students will produce. We ask them to do this on the whiteboards. And when they do this, they're using actually hypothetical deductive reasoning. They are reasoning like, if this explanation is correct and I do this, then this should happen. This is the way also how scientists reason. And they're using, as I said, multiple representations. In this case, they will use the sketches, which later we transform into the displacement position graphs, and then contrast them with the displacement time graphs for the waves. So then we really run the experiments, and as you all know what will happen, so these are the outcomes. So the testing experiment 1 is sending one large and one small pulse. The testing experiment 2 is sending two pulses with equal and opposite sign amplitudes. And the outcome of these experiments now, compared to the predictions, shows that we can reject the bounce-off explanation, but we cannot reject the pass-through explanation. It's very important that students at this point realize that we didn't prove that the pass-through explanation is correct. We only were not able to reject it. And then we can go on and try to refine this explanation. So now we know that pass-through is accepted as correct. But when we observe now again the original observational experiment, students will notice, and we point them to now look for details, they will realize that when they meet, the amplitude is about twice as large as before they met. So it looks like we can refine this pass-through explanation, that they pass through without infecting each other, but when they pass through, the total displacement is sum of the both displacements. So we add the displacements of each pulse together. Now, if this is correct, what would then be the prediction of what happens when the two opposite sign pulses meet? What should we have? A zero, huh? Zero. Yeah, no displacement. So that's an exciting moment because students, even when they did this experiment, they, especially in real time, they were not able to see details. So once they make this prediction, using now the explanation that they devised and improved, we can go and actually do again the high-speed version of the video, or they can use it in on the YouTube and observe. Okay, let's go to this moment. So it is almost zero, but not quite, yes? And some students are upset about this. They said, no, this is not then what we thought before. My explanation why they are so upset is that because science comes after math, and their experience with math is that if I calculate 2.7 and in the solutions it says 2.8, I'm wrong. But we know in science every interpretation of the number should be seen together with the measuring method. So, okay, so this is the opportunity for us to talk about something which is crucial in science, assumptions. So when we made the prediction that there will be a zero, what did we assume? That the shapes are exactly the same and opposite sign. But when we go now back to the same video, you can see that before they met, the shapes were pretty much the same, but not quite. And that's why also the subtraction was not complete. So what is here important is that assumptions are something that is really important in the practicing when scientists do science, but in schools we very rarely talk about assumptions, which are very important. So now is the time that the teacher brings now the name to this new model of wave behavior, superposition, and then go back to the original motivation. So if now we assume that the sound is some kind of a wave propagation, then we can have now idea how to cancel. We have to just emit the sound with opposite sign of the amplitudes to our eardrums, and if this sound is exactly the same as the sound that is coming from the environment, then we will achieve this canceling at our eardrum. We can come back to that later when we do sound, but the idea is here. So what I did now is a short activity which shows you how, it shows to students how scientists come from not knowing to knowing in the way that physicists, where they build new knowledge, really do it. And this was the approach created by Eugenia Etkina from Rutgers University, United States. And the name of this approach is called Investigative Science Learning Environment, or short ISLE, like a small island, ISLE. What I just did can be shown in a flow chart. So we started with a simple observational experiment. We asked students to identify patterns in this simple experiment. And then based on these patterns, they came up, or we helped them, we sometimes prompt them, with different explanations. Here, the ideas that students have to test their own ideas come into play that I mentioned before. What do we do next? We ask them to propose testing experiments and to make predictions for outcomes of these testing experiments based on the hypothesis that we are testing, before we run any testing experiments. Then we run testing experiments and we compare predictions with outcomes. And here, many things can happen. The process is not linear at all, not even cyclic. We can propose new, reject old hypotheses. We can go and test our assumptions. Often things don't match because we assumed something and we have to validate assumptions. Or maybe we even realized that we are not ready to make any explanations, and we said, let's go back to observations and do more data collecting. I would like to point here that although I'm talking about experiments all the time, they doesn't have to be experiments. Somebody will ask, what about in particle physics? How can I do experiments, or astrophysics? No, you can use data, the existing data. But those data can also have these roles that are here in red. So observational experiments, testing experiments. But once certain explanation survives several testing experiments, we are certain more and more about its validity. And now we can use this new knowledge to do application experiments. So these are typically problem solving and projects for students when they use the acquired knowledge to solve something and they are applying this knowledge. As I said, Eugenia Aitken was the original creator of this, and later Alan van Hevelen joined with her and improved that with some additional stuff. So multiple representations, as I already indicated before, are a very important part of scientists' work, but also we try to encourage students to use multiple representations. It has been shown by research that if students are using more than 2 different multiple representations, they are better in learning and grasping the ideas. What are multiple representations? From motion diagrams, force diagrams, graphs, bar charts, field lines, array diagrams, circuit diagrams, and eventually at the end, not eventually, but at the end, equations. So equations are also a type of representation, and words are also a type of representation. But equations should come at the end, after these graphical representations are practiced. And the other feature of IEL is that students are working in small groups and that they have opportunities to improve their work. This is especially important for if you want to have more women in science. I'll talk about this a little bit later. So IEL has been successfully used in different teaching introductory physics programs at all levels, also outside US, Sweden, Indonesia, Slovenia, at least that I know. Physics teacher preparation programs, like our program, also Rutgers program, and professional development for in-service physics teachers. I also run a professional development program. We call it continuous education program for in-service physics teachers. Every month they meet, and there the existing those who are teaching are learning also about this approach. Based on this approach, college level, so the algebra-based introductory physics textbooks have been written, and I had the privilege to be invited in the production of the 2nd edition, which just recently came out. And together with this textbook, there we have also the active learning guide. This is a collection of all kind of activities based on these ideas, and instructor's manual, and 150 and more videos which are freely available from the Pearson webpage. From 2012, we are gradually adapting IEL and Rutgers teacher preparation program ideas into our teacher preparation program. Of course, taking into account the strengths that I think we had before, experiments were always our strength, and taking into account the specifics of the Slovenian education system. So now I would like to share with you a few points about how this new knowledge affected our program. In what sense? I will be speaking about 2nd cycle program. So these are 2 years. After 3 years spending together with physics majors, our high school physics teachers go on 2-year program. And so I will be talking about this, but I think that all I'm saying here is applicable also to high school teaching of physics, as you hope you will see. So I split these changes into three levels. So first are those, let's say, simple changes that take little time, technical changes. So we first decided not to have classroom arranged in rows. We just turned around tables, so they are small islands, and this is the fixed geometry. Nobody is allowed to touch that. Students are only working in groups. And they are using whiteboards, which one of the teachers in US named thinkboards, and I like this expression. So these are the whiteboards on which students are writing their ideas. It's very easy to share then ideas. For the instructor, you go around, you quickly see where is which group, is there on the right idea or not. It's very easy then to call them and to organize the discussion. We are also using self-assessment rubrics for teaching. These are rubrics that we are using in different purposes, but right now I have in mind rubrics that students, future physics teachers, are using for preparing their micro-teaching lessons or their lessons when they teach when they do clinical practice in schools. Rubrics are came from Rutgers. I adapted them for our purpose. Rubric is a table, consists of several rows, and here I show you only one row. So each row describes one ability, but the columns describe to what extent this ability have been achieved. So, for example, ability to pose productive question. Well developed means that teacher is posing questions that are addressing some higher cognitive tasks, as shown here. That middle one is he is or she on the right way, but needs some improvement. And the last one we call missed opportunity. So this would be a teacher who is only asking questions that are requiring recalling some data. So, and the students are given these rubrics in advance, so they know how to prepare, and we are using these rubrics to score them. So it's much easier for me at the end of the student lesson, just hand him or her this rubric with marks where you are, and now you know how to improve. Change in language. So we do not use term demonstration experiment anymore. This was for me, I would say, the first thing that attracted me with IL. Those red names of experiments in that flowchart were observational, testing, and application experiment. I realized that looking at experiments in this way helps teacher much more to do the creative, active learning environment to engage students, because you are thinking about a role that this experiment will play in terms of what student will do, not demonstration experiment, which already with the name communicates that I'm demonstrating something to you and you are passive observer. So our students, when they do the lesson plans, they are not allowed to use the word demonstration experiments. We don't ask for predictions before observational experiments in purpose. So we only ask for predictions when students are able to make predictions based on hypothesis that they are testing or based on already agreed knowledge. So in other words, we are again trying to do the same as scientists do. If you would ask an astrophysicist, what chemotherapy should I use for this ovarian cancer? They will tell you they have no idea. This is not my field. And when we are asking students to make predictions, what will happen if I take a magnet and I quickly pushed it into the coil, and the coil is connected to the voltmeter, and the student never before saw or heard about a phenomenon induction? This is about the same thing. So doing something to just show student that he or she has no idea. The purpose of observational experiment is to find new ideas and then I'm able to make predictions based on either hypothesis that I'm creating or after I already have a suitable knowledge to make predictions. And we also don't use term misconceptions. We use term student ideas or student difficulties. This is a long, can be a long discussion, but I will tell you there are many papers now, research papers, that show that students actually do not have conceptions, that you change the context and they will give you a right answer. So if it is context dependent, it means it is not a robust conception. It means that students have some isolated ideas, resources, some people call them, which they activate depending on the context. And I think the most important argument why not using misconceptions, especially with future teachers, is that it communicates the idea that students are coming to our classroom with some wrong ideas which we have to erase. And what we know about the brain is that we cannot erase. It's better to build on existing. So that's why we rather call them difficulties, and in many cases it is shown that we only need to give the right name to shape a little bit idea which they already have. Sometimes it's enough to say, yes, yes, you are actually right, but what you have in mind in physics we call it momentum, not force. And everything can be right. So there are a lot of evidence and papers about this, and I just advise you to slowly change this word, which is very, very present, and I know it's hard to change the language. That's why it takes some time. And then there are changes that takes a lot of time. Students are given opportunities to improve their work. So this, at least to me, took a lot of time. I saw what they're doing at Rutgers, and I thought, no, I'm not doing that. This is not the purpose of our tests. And again, I'm emphasizing I have small groups. That's why this probably can be done in the way that I will show. But first, it was important to change my mindset. Why would I give student opportunity to improve the work without penalty if the student showed poor performance on the test? And Eugenia convinced me that this is good, and now I'm a great defender of this idea. So what I do, I give students a test. Students write a test, future physics teachers. And when they get tests back, they only get number of points that they achieved compared to the total number. Their rest of the test is not touched. So they have no idea where they lost points. I give them 24 hours of time to submit the improved version. They can talk to each other. Actually, I encourage that. It means that they discuss about something I want them to discuss about. They are sharing their ideas. They see where they come, where this guy was right and this girl was right, and I'm comparing, and now I see, probably I missed here. But when they submit the correction, they have to do also this. They have to write down in words, what did I do incorrectly, how to do it correctly, why did I make the mistake? So here I expect some reflection from them. And how did I learn? You can say, yeah, I learned from this guy, I learned from internet, I used several sources, I was not sure if this is correct, and so on. So all this, and if I'm not sure, I still allow myself opportunity to say, well, we can also see, and I'll give you some additional questions so I make sure that you now understand this question. So I have no problem if all my class have A at the end, but I know that they will all go from our program as teachers with a solid knowledge. What is the benefit of leaving people through the program with bad grades and knowing that this will be now a teacher and will have impact on so many students later in her life, and he will be bitter if they don't have a solid knowledge. So this took me a lot of time. Every meeting ends with students' reflections. This was also hard. Students have to, I take 10 or 15 minutes at the end to discuss what they learned as a physicist or as a teacher. And I don't know how it's in Ireland, but Slovenia was part of Austro-Hungarian Empire, and those countries were have something in common in educational systems. Also, Czech Republic, Slovak, Austria, Hungary. That teaching was very traditional, and discussion was not part of the teaching process, learning process in the classroom, as opposed to the United States. So, first reflections were horrible. I was pulling out from students. They didn't know what I mean, but gradually we came up, and now they are doing it. So it takes some time. And students are using that framework that I described before in their master thesis and PhDs. And now I will, as an experimentalist and somebody who really like to use experiments in the classroom, I would like to share with you how the new way of looking at the roles of experiments helped me more get out of experiments. As I said, the experiments in IL have 3 different roles, and we can identify these roles in the history of physics. If you look history of physics and search through the experiments, you see that they can be categorized in one of these 3 groups. Actually, this is the way how Eugenia came up with this first idea. And I will show you now an example of experiment that I was very proud and used a lot of times and wrote papers about it before I learned about IL, and I'll show you how I changed after that. So this is so-called light cone experiment. Anybody knows about this experiment? Hands up. You know? Okay. So what I do, you take a fish tank with a glass bottom, put a white paper under the bottom, and you point a laser. The best is a green laser. It works also with red, but we see better in green. Down to the vertically down to the through the water to this paper, which is below the bottom. And what you will observe is this beautiful cone that appears, very clear light cone. And when I saw this first time, I needed quite some time I had a slight idea what's going on, but to come up exactly to the complete understanding, it was like one day that I was playing with this, and what I was doing, I was testing my ideas with different additional experiments. And yet, I thought, well, this is a perfect experiment that I will show to my students when we do geometrical optics at the end, to show them how physics is so powerful, how all this we can explain, and this matches with the theory we develop and all this. So I would show them this as a demo experiment, and then carefully explain and even invite students to participate in some parts. What happens if the ray hits the glass at almost 90 degrees? How would it reflect in, and so on. So this is all described in a paper which you can find in the American Journal of Physics. But later, when I met these IL creators, we decided to give this experiment to students as an open-ended. So here it is, observe and try to explain. And that's how another paper, this paper appeared. This is a paper in the American Journal of Physics which describes what students do. They come up with different ideas. They think that this cone is the result of the scattering on the paper, that the fish tank is there just to make it visible. They think that maybe this is the result of scattering at in the glass. And those who think about refraction and total internal reflection, even those have 2 ideas, one correct, one incorrect. Something that the cone is the result of refraction on the air glass interface, and something that it is the result of the glass water interface. What they do create testing experiments. So this is observational experiment, and these are all kind of testing experiments. They put paper there, just point laser, tap some chalk and dust, and see, is it really there a cone if only paper reflects the light? They put black paper under the fish tank, and the cone disappears. They wet the paper under the fish tank, and the cone disappears. They even change the solution. They change, if they use the sugar water solution, and for this you need to take a photo because the change is not very huge, but it is the cone angle change. So all this helps them to finally come up with a clear understanding. And I realized that it was really missed opportunity for me to show them this as a demonstration experiment. It's much better to save that for their personal investigation. And we used that also in another research. We thought, well, if it took me about an hour or 1/2 a day to go through all this, we can use this in the research where we were interested in how do experts solve experimental problems in real time. We put different experts, theoretical physicists, pharmacists, experimental physicists, in pairs, and we gave them this problem and videotaped them and then coded the whole session, and they needed about an hour to completely solve the problem. And there's a paper about it, but the main message of this paper is that IL as a process, which I showed you before as a flowchart, describes adequately also what scientists, experts do in real time, and we put them in pairs so we could record their thoughts. If we have a single person, of course, we don't know what's going on in their minds. So this is one of the techniques. And now when we have this knowledge, we put this into the active learning guide that I mentioned before. So this is the unit in the active learning guide. Tested, we know exactly how to frame questions, what to ask from students. So the first part in small font is just introduction, and then these are the questions for students. And finally, the last part, and this is partly also touching the topic of the previous speaker, new types of problems. So you've heard a lot about how the problems are used in examinations, but now if you think problems should reflect our teaching, and our teaching is subject to different changes in the whole society, driven by research, also by changes that are expected from the labor market and so on. So eventually, if we are supposed to develop epistemic knowledge, then also our tests and our problems should test this sort of a knowledge. And so when we were writing the second edition of that book that I showed before, I was involved in creating new types of problems. I'm not the author of the types, but I was trying to use these known types and do the problems that would evaluate this kind of a new abilities. So what I mean by new types of problems here is to go beyond the problems that can be solved only by searching for the right combination of formulas, or the problems that have exactly the needed number of givens and all the assumptions there and ask for one numerical answer. Here is a problem. I will describe you, don't have to read. There are 3 students and they are investigating how snow stops a bottle of juice that is dropped into the snow, and in particular they were interested how the force exerted by the snow on the bottle depends on the age of the snow. So to determine that, they take the bottle, dropped it into the snow, and they took a high-speed video of that and then produced the graph that shows how the velocity of bottle from the moment when they touched the snow was changing until the bottle stopped. And this is the graph that they produced after 4 days and after 6 days, 6 and 4 days after snow. And now these students are discussing. There are 3 students discussing what this results. So Lucia says that 6 days snow exerts larger force on the bottle because it stops in a shorter time. Isabel says that time is not enough to determine about force, but you have to look for the slopes of the lines that fit that points. And Austin says that they cannot compare this because the initial velocities are different, and they should run the experiment again, making sure the velocities are equal. And now students are asked to comment on the student's suggestion and decide which one, if any, is correct. So here commenting means saying something about each statement, saying also what part is good and what part is not good. So this is a discussion. And what we expect here is that they realize that the first one is incorrect, the second one is correct, but correct assuming that the velocity doesn't affect the force, so that force exerted by snow is independent on the velocity of the bottle, which is essentially the message of the last one. So first one is incorrect, second is correct, but the third one points to a certain important assumption. And this is the type of the problem where there's not just one correct answer, where we see how students see to which depth, and different students will go differently deep. But also research shows that girls are better than boys in looking at the same situation from different angles, that they are more able to put herself into the different views and judging about one situation from different angles. So this kind of a problem develops ability to critically evaluate the reasoning of some other people, develop critical thinking, ability to listen, which is important, and to focus on other people's ideas, but also to recognize productive ideas even if they are embedded in incorrect answers. I think this is one of the very important things for teamwork. How many ideas contain very probably crucial or useful elements, and we are just abandoning them because we don't like the first statement that person said. And here another problem, two students are pushing the little squishy piglet along the floor and observing how the piglet is slowing down, make the table how the distance traveled and time needed to stop what they measured. And now the task of the student is to say, do this data support the hypothesis that this is a constant accelerate motion? So now students are in a position to test the hypothesis or see if they make judgment. If this data are supporting the hypothesis, what they eventually do, they think if they realize that if the piglet was moving constant acceleration and I draw a distance versus time square graph, then the graph should look like a straight line. And from this slope of the straight line, they can also get the acceleration. And finally, just one problem that actually emerged from me observing students doing experiments. They were using a white LED as a point light source and comparing what they see in certain other experiments, but they noticed that if they put a convex or concave lens, we get a different pattern on the screen. And they were trying to explain that, and I realized how difficult was this for them because they were only used to do those 3 rays. And here you have to do all rays. You have to think also connect the ray picture with the intensity on the screen. And it's a really nice example of problem where students have to use knowledge in a different situation. So this sort of problems develop ability to combine, switch between representations, but students also learn how to use some simple equipment either to do some research or do the problems. So I'm at the end of my talk. I would like to just summarize a few main ideas. It's our duty not only to help students learn physics concepts, but also to help them learn like physicists. My experience is that looking at experiments as observational testing and application experiments help students to think like scientists, but also help me as a teacher to actively engage students to make classroom more active, to do active learning. And my experience is also that it's better to prepare future teachers to be proficient in one approach than to expose them to different approaches and expect that they will use one of them when they go to the classroom. And thank you very much for your attention.